Hey, it's Dr. J. Today we're going to learn about marginal analysis, one of the key components to differential calculus, and in particular business calculus. So when we have spent a lot of time talking about the derivative, we're going to be able to use the derivative to help us analyze, profit and revenue and cost and all of the business type terms and functions that we have discussed previously in this course. So before we actually begin doing the business math, first I want to just review the derivative rules. Just a brief review of those rules, because the last video, I didn't really have time to summarize everything. I just kind of was hacking through them all one by one, and I'd like to see them all in one convenient location, maybe do a few examples. And then when we're done with that, we will do some business math, okay? So here are the rules. The first rule, the derivative of a constant is zero. It's probably the easiest of all the rules. The second rule, the derivative of a constant times a function is the constant times the derivative of the function. Yeah, that one we use quite a bit. Yeah. The third rule, the derivative of a power function, x to the n, the nth power, is n times the same variable, x, raised to the n minus 1 power. That's probably one of the most common types of functions that we will see. So when I say f of x could be any function. We have lots of different types of functions. In this rule, x to the n power is one particular type of function called a power function. All right. The fourth rule, the derivative of an exponential is the same exponential times the natural log of the base. And then I like to say 4 star, that's a special case. The derivative of e to the x is just e to the x because the ln of e is 1. So we call this the special case of Rule 4. We can call that Rule 4 star. In order to save space here, I want to try to get all of the rules in one board. I'm going to just say the answer here, e to the x. The derivative of e to the x is just e to the x. 5, the derivative of a logarithm log base b of x. Well, that is 1 over x times the ln of b. Okay, and then we have 5 star, special case. The derivative of the natural log is just 1 over x. Again, because when you take the natural log of base e, this natural log of e would just be 1. All right, so technically it's like this, ln of e, but ln of e is just 1. And so we typically just don't write this because it's just multiplying by 1. And so when we're doing our calculus, we will just simply write 1 over x. In other words, when I'm doing a problem involving this, I only write the natural log part in the answer if the base is something other than the natural base. Okay. I wanted to get them all onto one page, so I guess I'll put 6 and 7 up here. All right, so we got 1, 2, 3, 4, 5, 6. Oh, 1, 2, 3, 4, 5. And remember, 4 and 5 have these extra special cases. Sorry, my head is blocking number 4, so. 4 and 5 have these extra special cases. 6 and 7 can actually be combined together into one rule because they are basically the same rule. Yeah, it just says the derivative of a sum of functions. You're adding functions. You just take the derivative of each function individually and then add the result. So 6 and 7 are duplicates of each other, just changing the plus to a minus. So you can just kind of memorize these as the same rule, sums and differences. So there's a couple things that you should notice that are not in these rules. If the sum or the difference was multiplying or dividing, yeah, that rule is not an introductory rule. That's a more exotic rule, substantially second level beyond the basic introduction. So let's do some examples and let's just see how these rules play out in everyday practice. Okay. The numbering is not all that important. It's not like a standard numbering. It's just the numbering. This is the order in which I presented them. So these are the first 7 rules, if you like. Okay, so I'm about to erase them all and get right into some mathematics. Let's start with a function written just in standard equation form. And this is a rational function. So we have a rational function. It's a division of 2 functions. And so since rules 6 and 7 only apply to adding and subtracting, yeah, we can't simply take the derivative yet. All right. Because there is no rule that says you can take the derivative of the top or the numerator and then take the derivative of the denominator and divide the 2 answers. That's just not a rule, right? So in order to apply rules 6 or 7, I think that we're actually going to apply rule 6 because this one's all adding. It's all addition. So we're going to first rewrite it. So that we do not have a denominator anymore. So this is going to be 4x squared over x to the 1/2 plus 7x over x to the 1/2 plus 8 over x to the 1/2. So we're rewriting the square root as a 1/2 power. Then we're going to divide by subtracting the power. So the first one becomes 2 minus a half, which is 3 halves. The second one becomes 1 minus a half, which is just a half. And the third one's kind of strange because it's technically 8x to the 0 power. So the new power is 0 minus a half, which is negative a half. So first we have to rewrite it, and now we can take the derivative. All right, so you have several steps of prep work. So now we can apply rule number 6. We'll actually apply it twice. The rule says you can add 2 functions, right? Well, if you can add 2 functions, then you can add 3 functions or 4, any number of functions. So you can, what we call that, expanding the rule or repeating the rule over and over again. All right, and so now we're going to do the derivative of each one of these, right, separately. So the derivative of the first one is going to be 4 times 3 halves x to the 3 halves minus 1. Yeah, the 4 is the constant, comes out in front. Then I apply the power rule, also known as rule number 3. So this is a combination of rule number 2 and 3. The 7 comes out in front. 1 half x to the 1 half minus 1. Now this one, 8 comes out in front times negative 1 half. Be careful with the power. X to the negative 1 half minus 1. I'm just going to copy the whole thing again because I want to make that very clear. And this is really just for me to keep track of where we are in the problem and for you to have a moment to look at what I've done so far. All right, let's see where we're at now. So this is, I just copied everything again. I have, from here to here, I haven't done anything yet. Just make sure everything matches. Sometimes when I move all my stuff to a new position, I'll lose something. I have to kind of double check. Everything look good? Okay. So dy dx, 4 times 3 halves is going to be 6. I feel like we've done that before. 3 halves minus 1 is 1 half. 7 times a half is just 7 halves. It's going to be x to the negative a half. So I'm first just messing with the powers and the coefficients. Powers and coefficients. This is going to be negative 4. That's the coefficient. And then x to the negative 3 halves. That's the power. Okay, that is the answer. You could type it in, but I like to simplify. On homework, you feel free to experiment with different, versions of the answer. I like to simplify. I like to tell students to simplify. So if the question asks to simplify, which generally I do, sometimes it'll slip by me and I'll forget to ask, but it's kind of common courtesy to simplify whenever possible. So simplifying means getting rid of all the negatives and the fractional exponents. It doesn't mean get rid of all fractions. It just means get rid of all fractional exponents. So this is your simplified answer. It means the same thing as the previous step. It's just simplified. So x to the 1 half is written as the square root of x. X to the negative 1/2 is the square root of x in the denominator, because the power is negative. And then x to the negative 3/2 is the square root of x cubed, 3/2 x cubed, and then written in the denominator. And so that's your final answer. All right. That's it for example 1. So again, I'm not going to do anything with these derivatives for the time being. I'm just going to exercise some of the rules that we didn't get a chance to see in the last one. We might need some of these when we get into the business applications. Let's do another one that's division or a quotient of 2 or more. This is 4 terms in the numerator divided by 1 term in the denominator. And again, I want to make this very clear why we must prepare this for differentiation. So before we can find the derivative, we must first get rid of the denominator. We cannot take the derivative the way it's written right now. We don't have a rule for that yet. So I'm rewriting first. All right. And then I will calculate everything. So I've got 6x to the third over 8x squared minus 32x squared ln of x over 8x squared plus 24x over 8x squared minus 48 over 8x squared. So if I were you, when you see this problem on the screen, don't even write that problem down. Right? I would just jump straight to this when you start doing your math, if you're doing this on paper. So 6/8 is going to be 3/4. And then x to the third, x to the second is just going to be x. 3/4 x. 32 divided by 8 is going to be 4. The x squareds are going to cancel, and I'm going to get ln of x. 24 divided by 8 is going to be 3. And then the x in the numerator will cancel, but the x in the denominator will still be here. And then I'm going to say 48 divided by 8 is 6. And the x squared will still be in the denominator. Now, I need to get rid of the x in the denominator. I don't have to get rid of numbers, like 4. 4 is okay in the denominator. It's the variables that we have to get out of the denominator. So I'm going to rewrite this as 3x to the negative 1. And negative 6x to the negative 2. You can't have any variables in the denominator because we don't have a rule yet, I should say yet, on how to deal with that. So now we can take the derivative, y prime. This is just a shorthand for dy dx. So sometimes I'll say y prime instead of saying dy dx. Just a quick way to say take the derivative. All right, 3/4 x. So the derivative is just 3/4. So we don't worry about denominators when they're constants. But now the derivative of x is just going to be 1. So that's 3/4 times 1. Now here, 4, constant, comes out in front. Now what's the derivative of ln? That's that special case, 1 over x. Here, bring the 3 out in front. And then do the derivative of x to the negative 1. That's going to be negative 1 x to the negative 2. Yeah. And then for the last one, negative 6 times negative 2 times x to the negative 3. And I think I can clean this one up right here, if I could squeeze it in. 3/4 minus 4 over x minus 3 over x squared plus 12 over x cubed. And that is your final answer. So 3/4 minus 4 over x minus 3 over x squared plus 12 over x cubed. And I got that all in one attempt. Okay. Moving right along, just using the rules. Taking derivatives. Example 3. Back to the F notation, one of the more common notations that we've had. All right, this is kind of an awkward looking function. Let me put the fraction bar a little bit straighter. So this one only has one denominator. All right, one denominator. But it does have a product, right? We have x to the 6th, and there's an invisible times right here and here too. These are invisible. We call these implied products. So whenever you see two functions written right next to each other, or two operations written right next to each other, or two objects of any mathematical nature, we assume that it's implied that they're being multiplied, right? And again, we don't have a rule for that, right? We have a rule for adding, we have a rule for subtracting, but we don't have a rule for multiplying functions together. So I have to get rid of that product before I can apply the rules that we have. So again, let's just rewrite this using exponents. So x to the 1/2 is the square root of x. X squared is x to the negative 2, yeah, because it's in the denominator. And then another product, x to the negative 1/2. So because these are in the denominator, say denom, in the denominator, they're positive. Yeah, I mean, they're negative. They're positive when they're in the denominator, but when you bring them up to the numerator, they become negative. These ones are not in the denominator, so they do not become negative. They just stay whatever they are. All right, so one more step, and then we're ready to differentiate. So this is 6 plus 1/2. Yeah, 6 plus 1/2, which is 13 halves. I'm going to say DIY. DIY. 6 plus 1/2 is 13 halves. Do it yourself. All right, I'll give you a hint. 6 is 6 times, sorry, the hint is 6 times 2 is 12. That's the hint I'm going to give you. All right. Similarly here, you're going to add these guys, you're going to get negative 5 halves when you add these two. And again, I'm going to say DIY. Do it yourself. Negative 2 plus negative a half is equal to negative 5 halves. Do it yourself. All right. And now we're ready for the derivative. So the derivative is the next step. So we're going to use the power rule. That's going to be 26 x to the 11 halves minus 25 halves x to the negative 3 halves. And then to clean up our final answer, 26 over the square root of x to the 11th minus 25. Oh, sorry. Oh, I got too carried away. There's no fraction in the first one. The fraction only occurs with the negative power. 25 over 2 times the square root of x cubed. And that's your final answer. A couple things you should probably double check. When you multiply 13 times 4 and then divide it by 2, so 13 times 4 divided by 2 becomes 52 divided by 2, which becomes 26. I tried to do that without the calculator. I do have my calculator handy if we need it. I didn't need it in this example. So that one was kind of tricky, how I got 26. And then when I subtracted 1, I got 11 halves. And then similarly here, which I just noticed a mistake. I'm glad I'm talking about that. That should be a 7, not a 3. So I'm glad I talked my see, by talking through the answer, I can find little mistakes. When I subtracted 1 from the 5 halves, because it's negative, it goes to 7 halves. So make that correction in your final answer, and now I stand by my answer. I should also mention that the only reason why I'm leaving this 2 in the bottom is because 25 is not divisible by 2. If 25 was divisible by 2, then I would even go one more step. All right. Using the rules. I'm also showing all the different notations that we might be using as well. How about this one? 1 over 12x to the 4th minus 5 halves x to the 2nd plus 15 times the cube root of x plus e. All right. So again, I mentioned this earlier. I would read this on the screen if I were you, but then when I would write this down, I would immediately write it down as 1/12 x to the negative 4. Because you got to get that x out of the denominator. And then I would also rewrite the cube root as 1/3 power. All right. And then now you can take the derivative of f of x. Again, this is the same thing as f prime. Just another way to say f prime. This one's not too bad. Right? Again, I call this bread and butter. Yeah, this is just basic algebra steps here. So I've got negative 4 times 1/12. So that's going to be negative 1/3. And then I subtract 1. Be careful. Subtracting 1 from a negative, it's going to go down to negative 5. All right, here. 2 times negative 5 halves. Well, that's just going to be negative 5. And then subtracting 1 from 2 gives you a power of 1, which you could leave off the power of 1 if you choose. 1/3 times 15 is 5. Subtract 1 from 1/3, you get -2/3. Now this one, be careful. Yeah, we do have that special case that we talked about, or that I wrote down very briefly at the beginning, that the derivative of e to the x is e to the x, right? It comes out to be exactly itself. But this is not e to the x. This is just e. So that's rule number 1. So be careful. Sometimes rule number 1 is not obvious. We use it a lot. One of the reasons why it's rule number 1 is because it shows up quite often, but it sometimes shows up in disguise, right? You're not sure, is that really a constant? I thought it was a function. Well, if it doesn't have an x, it's a constant. So that's just rule number 1. Yeah, the derivative of that is 0. And so our final answer, the derivative of f of x, also known as f prime, aka f prime of x, that's just another way to say that, is -1 over 3x to the 5th minus 5x plus 5 over the cube root of x squared. Not the square root of x cubed, right? It's the cube root of x squared, because see, the 3 is in the denominator and the 2 is in the numerator, so it's the cube root of x squared. And that's your final answer. And again, we're not graphing these. That would take a whole nother, lesson. In fact, it's going to not, graphing these is not going to appear until chapter 3. So for now, I'm not going to spend a lot of time plugging in numbers and trying to get points or any of that. Not on this type. If we're going to plug in numbers, it'll have to be a much easier function, like example 5. So let's plug in a number now, all right, which means I'm going to need my calculator handy, and I'm probably going to need my scientific version of the calculator. So we're going to evaluate f prime of 3. So first we need to do f prime of x. So that's going to be 25 times the derivative of 2 to the x. Yeah. I guess I wrote it this way. I'll keep it written the same way. It doesn't really matter where the parentheses are, though. Although I shouldn't say it so strongly. If the parentheses were around the 25, it would mean something different. So the parentheses are around the 2 means that this exponent only applies to the 2 and not to the 25. So I guess the parentheses do matter, but they don't matter when you get to this step, because it's just going to be 25 times whatever I get from my recipe. So let's look at the rule now that we had earlier. I think this was called rule number, I don't remember, 6? No, 5. Yeah, it was rule number 5. No, rule 4. I told you the numbers don't really matter. It was one of the rules. It was the rule of exponential functions. So the rule says 2 to the x power times the natural log of 2. So this is your exponential function derivative. And now to do f prime of 3, just plug in 3. That's what we mean by evaluating. And this is where you're going to need a calculator. It's going to be 25 times 8 times the ln of 2, 25 times 8, I believe, is 200. Do all your constants first. So now you're going to go, all right, ln of 2. So I put the 2 in there first, and then I hit the ln button. So that's the ln of 2. So do that, and then multiply it by your constant times 200. And let's go ahead and round this to 2 decimal places. When we do our business math, we typically like cents. So a very common instruction is to round to the nearest hundredth. So that means we go to the 3rd decimal place and we use the rule. Because 9 is greater than 5, we're going to round that up. And that's going to be 138.63. So in the topic of marginal analysis today, which I haven't quite got to yet, I'm about ready to get there very soon. Maybe one more example. These were all examples that I wish I would have covered in the last video, but I ran out of time. So here we are doing it now. All right. But this does actually lead right into what we're going to do in business. This is like a dollar amount, right? This is $138.63. So this is exactly how we're going to perform marginal analysis as soon as I tell you what marginal analysis is. But this answer would then be interpreted typically as money, $138.63. Now, what does it actually mean? I just have to wait one more example to get there. I want to circle back to the very beginning of derivatives and what a derivative tells you. It tells you an instantaneous rate of change. The most common function that you will see in this course is a quadratic function. It's such a natural application. It has such natural applications in business, and you'll see a lot of different functions that have the same sort of format, right? You have a squared term, you have a first degree linear term, then you have a constant term. So we call that the ABCs of algebra and of calculus as well. So circling back to the beginning of chapter 2, what was a derivative telling you? It was telling you the slope of the tangent line. Yeah, in other words, the instantaneous rate of change, the IROC. Yeah, that's what the key question was. Finding the slope of the tangent line. And I just want to make sure that before we move on to the business of business calculus, that we don't forget where we came from, right? This same question was asked, and I would have to give you a value. So let's do x equals 6. I give you a value. I have to tell you where I want the slope at, right? And think about where we came from with all the limits and the graphs and the tables and the estimating and so many different calculations that we did. But watch how easy it is now. First, you find f prime of x. And look at how easy this is. Boom. Done. Yeah. And that's how quickly you're going to do it when we get to the business applications. You take the 2, you multiply it by the -5, that gives you -10. You subtract 1 from the x squared and you get x. Yeah, that's easy. 40x, you ignore the 40, yeah, pull it out to the front, not all the way to the front, but out in the front of that term. Then you take the derivative of x. Derivative of x is just 1. So technically this is 40 times 1, but nobody ever writes the times 1. Well, you might write it once and then never write it again. And then finally, the very first rule that we learned in the rules of differentiation, derivative rule number 1 is the derivative of a constant is 0. So there you go. There's your derivative. And now to find the slope, say m, you just plug in the number that was asked, and there it is. And it's almost like, where were you a month ago with this, you know? Well, you know, if I would have told you this a month ago, it would have made calculus almost seem too easy. You know? It plus would have made you think that that was calculus, right? So calculus is taking a limit. That's calculus, right? If you're not taking a limit, you're not doing calculus. But once you've taken 100 limits, then you can start doing it this way because you understand the principle, right? Again, I want to always go back to elementary school. You know, if you never learned how to add, right? Suppose they just skipped adding, right? As children, right? You could do that. You could just skip adding and go straight to multiplying and just tell people, you know, 4 times 5 is 20, right? And the little kids would memorize 4 times 5 is 20, right? But if you never taught them how to add, then the answer 20 wouldn't really mean anything, right? They would just be memorizing that somebody told them 4 times 5 is 20. But you, as intelligent, educated adults, if somebody tells you, you know, 4 times 5 is 20, or perhaps the other way around, you tell your children or somebody 4 times 5 is 20, you as an intelligent person know that it means 5 plus 5 plus 5. Yeah. If you also probably know that it means 4 plus 4 plus 4 plus 4, so that there are actually 2 different ways to achieve the same result, which is, again, what I do every day on these videos. I show you several different ways of approaching the same concept. And that is the true definition of being educated, right? Anybody can just give you an answer, right? You ask me a question, I can just tell you the answer. But I want you to know where that answer comes from, why that answer is important, and more importantly, how this is going to help you in your career and your education. So, having said that, let's move on to business. So this is the topic of the day, marginal analysis. These questions are pretty detailed, so we will, you know, limit them to some basic types. We have price demand. Okay. We have revenue. Remember, revenue is equal to the price demand function multiplied by X. So if you have the price demand, you take that function, you multiply it by X, that gives you the revenue function. You have cost, and then you have profit. And remember, profit is revenue minus cost. All right, so price demand gives us revenue. Then when we have revenue and cost, the revenue minus the cost gives us the profit. So these are the functions P prime of X, R prime of X, C prime of X, and P prime of X are called marginal functions. Marginal functions. The derivative, oh, this is kind of scary because the profit and the price both look like P's. I should be very careful here. Profit is capital P. And price is lowercase p. Be careful here. Right, so these are marginal functions. In other words, they measure the rate of change and we call that the margin. Yeah, how much is it changing? Right? Let's get right into it and just do an example. All right. So when I say marginal, right, marginal analysis, I basically mean take these functions, the ones that we've already talked about, and take their derivative. And this is what we mean when we say applying marginal analysis. All right. So we'll say the marginal cost, or the marginal profit, or the marginal price, or the marginal revenue. Example 6. A small business uses the price demand function so this is already given to you. Price demand function of 150 times 0.975 to the x. Where x is the number of units sold. Okay. P of x is the associated price. Yeah. So generally speaking, again, I'm not really going to get super detailed, but P is the price. Again, lowercase p. It's very difficult to draw those carefully. X is the number of units sold, right? And then as you sell more units, the price goes down. Okay. Sometimes it's a straight line. In this particular case, it's a slight curve. It's an exponential function, so it has a little bit of a bend to it. It basically means that the price will never actually be zero, right? So the price will get lower and lower and lower like this, but it won't ever actually be free. Yeah. One of the problems with the linear price demand is if it's a straight line, it hits the axis, and that would mean that you're giving it away, which is not really very realistic. So this is a different type of model that more accurately depicts the price and demand. I have not shown you how to construct one of these, so for now, I have to give them to you already pre-constructed until I teach you how to make one of these yourself. All right, so let's get right into it. What do we like to know? Find the marginal price, P prime of 15. So in other words, I'm saying if 15 units are sold, what would the associated price be, right? But remember, it's the marginal price, so it's the rate of change in price when x is equal to 15. So we're basically asking for the slope of that line right there, of this little tangent line right there. My graph is not an accurate representation. It's just to give you a general idea, so there's a tiny little line right here. All right, let's go ahead and do it. Let's first find P prime of x. This is the marginal price function. All right. So P prime of x will be 150 times 0.975x times ln of 0.975. That's because this is an exponential function. 150 is the constant. This is my a, 0.975. And then I multiply by ln of a, whatever that is. And now I plug in 15. 150 0.975 to the 15th power times ln of 0.975. Definitely going to need a calculator for a lot of these. So I've got 0.975. I'm going to use my y to the x button here. Y to the x. I'm going to raise it to the 15th power. All right, that gives me this. Then I'm going to multiply it by 150. Now I'm going to write this down just in case I lose it. 102.603102, blah, 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 blah. That's probably enough. All right, that's just in case I lose it. I might not need it. Now I'm going to do my ln. So I'm going to go 0.975 ln. And I lost it. So now I gotta start over again. 0.975 ln. All right, there it is. Negative 0.025317, blah, blah, blah. All right, I'm not going to lose it this time. Times this thing, which I'm glad I wrote it down, 102.603102. And that gives me approximately negative $2.597, which we're going to round to the nearest cent. That's going to be $2.60 negative. That's that rule where, see, the 7 is bigger than a 5, so it rounds the 9 up to a 10, and then rounds the 5 up to a 6. That's sometimes called double rounding, or the rounder bumps the next rounder up to the next level, bumping or carrying, whatever you like. So, I mean, maybe if I draw a larger diagram, it might make sense. You have this sort of curve here. Your x is 15. This is your x-axis here. And then you have a line right here, tangent line, and the slope of this line is negative 2.60. Or you can just say negative 2.6, same thing, $2.60. We typically draw it as a line, but I sometimes like to omit the tail and just think of it as only moving in one direction. So it's like a little vector. Right? And it tells you something. It tells you P prime of 15 can be interpreted equals negative 2.60 means that when 15 units are sold, the price, by the way, the name for this is demand, yeah? So we sometimes say 15 units are demanded, right? In other words, the customers are demanding 15 of these things. It's a small company, right? They're not selling very many. The price is decreasing at a rate of $2.60 per unit. So the price will be going down, yeah? Which makes sense, right? Because as you go to the next unit and the next unit and the next unit, the price is going to keep shrinking. Okay. Next example. That's the end of that one. That's price. Notice we haven't actually sold any of these things yet. In order to make a profit, we need to be able to sell things. And we also have to pay for the things that we sell. So let's get into profit now. Example 8. So, I don't know, a company sells ice cream. The cost to produce it is to produce each gallon is given by 5x plus 441. So again, so each gallon is costing me $5 to produce. Yeah, and this is in dollars. Plus $441 in fixed costs, right? This is expensive ice cream. Yeah. So handmade organic ice cream. The price demand is PX equals negative 0.04x plus 8. Now, this is a more traditional price demand function. It's just a straight line. Yeah. We don't typically take the derivative of a straight line. I mean, you could take the derivative of a straight line, but it's not very interesting because it's a straight line. The slope is always the same. So you would always get this value. So I'm not going to ask that question this time. Right? This time I'm going to ask for the marginal profit when 18 gallons are produced and sold. The marginal profit when 18 gallons are produced and sold. So profit's that fancy P. Yeah. You don't have to write a fancy P. You can just do a regular capital P, but be very careful. It's not the same as this P. This P and this P. So capital P is not the same as little p. They mean something different. All right, so remember what capital P is? Capital P is revenue minus cost. And I like to put an extra set of parentheses around the cost just to be safe. Revenue is price demand times X. And cost is 5X plus 441. Price demand is 0.4x plus 8. So price demand times x is 0.04x squared plus 8x. So remember, to go from price demand to revenue, all you do is multiply each term by x, and it turns it into a quadratic equation. The reason why I put the extra parentheses here is because you're going to subtract 5x, and then you're going to subtract 441. So having these extra parentheses really helps. So my profit function is negative 0.4x squared plus 3x minus 441. That's my profit function. All right. So find the marginal profit. Well, first we have to find the marginal profit function, which is the derivative of this thing. But that should be pretty easy, right? This is, again, bread and butter, right? You just multiply by 2, multiply the constant by 2, subtract 1, so the power is just x to the first, and then remove the x from the middle term, it's just 3, and then throw away the constant. The constant becomes 0. So this is your marginal profit function. And then if we want to know what is the margin of profit, marginal profit when 18 gallons are sold, 18 gallons of ice cream are sold, just plug in 18. Not too bad, huh? I mean, once you have the function, you take its derivative and then you apply the derivative. So you got negative 0.08 times 18 plus 3, and that is positive $1.56. This one came out nice. I didn't even have to round it. Round it itself in the process. So what does this mean? When 18 gallons of milk, or ice cream, whatever. I guess before it was ice cream, it was milk, I guess. When 18 gallons of ice cream are produced and sold, the profit is increasing at a rate of $1.56 per gallon. We usually say $1.56 when you're talking to somebody, $1.56. But in math, you just call it $1.56. That's just the way we write it in math. It is $1.56 or $1.56. We don't say with. We don't say $1 with 56 cents. That's bad form, bad mathematical form. So you can say $1.56. You can say $1.56 if it's understood, or you can say $1.56. That's typically the way I prefer it. $1.56 per gallon. All right, that's kind of cool. The profit is increasing. That's good. Yeah. If you're selling ice cream, that's a good thing. As long as the profit is increasing, you want to keep producing, right? If at some point the profit starts going down, you actually are better off stopping production. Stop, because now you're producing, and your cost to produce it is outweighing the benefit of the revenue that you get from selling it. And so remember, profit is revenue minus cost. And if that turns upside down on you, upside down meaning negative, right? Then that means it's not worth it to keep selling ice cream. It's a little bit counterintuitive, right? You would think, just sell, right? Well, not always. Sometimes you got to know when to put the brakes on, but not yet. If this was my company, keep on selling. That's how we want to make predictions about things. So before I do the last couple examples, I just want to talk a little bit more about what that $1.56 means, right? The profit earned on the nth unit, or item. Sometimes I call it an item. Depends on what it is. The technical term for it is unit. Is P prime of n minus 1. So let's just save this. Note, if n was 19, then n minus 1 would be 18. And P prime of 18 was $1.56. And so this represents margin. Yeah, we call that the margin. Represents the profit earned by selling the nth unit. Let me say the additional profit. Extra profit. That's a better word. That's what we call the margin. Right. So think about what that means. So what you're doing is you're saying, well, if I sold, so P prime of 18 is the profit from selling the 19th gallon of ice cream. That's what that means. We're saying the profit is increasing at a rate of $1.56 per gallon. I've already sold 18 gallons. Yeah. If I sell 19 gallons, the 19th gallon, just that 1 gallon, earns me an additional extra profit, $1.56 for selling that 1 gallon. And there's an interesting pattern that happens. So you have sort of this X and PX, yeah, and you're at, say, 18. Right. And so the graph kind of looks like this. You start off negative 441. You're sort of in the hole, $441. You sell, yeah. And then at this particular point, at 18 units, it's adding an additional $1.56 to the total profit. So let's call that a total. It doesn't mean that this number is $1.56. That's why it's called the margin. So this little thing right here is called the margin. See how it kind of looks like a margin? So you already had a certain amount of money. Yeah. If you're curious what the total is, before I erase this, the total is P18, no calculus required. You would just take the profit from selling 18 units, no calculus. So that would be negative 0.04, 18 squared plus, oh God, what was the middle term? 3 times 18 minus 441. Good thing I remembered the function. So then you would say 18 times 18 is 324 times 0.04 negative. So that'll be negative $12.96. It's not a lot. This is like a small business. 3 times 18, $54. Oh, my graph is totally wrong. Minus 441. Oh, I'm glad this happened then. I can just move the x-axis here. Now that we know where we're at. See, I just wrote total thinking that we had made some money already, but when this doesn't even require calculus. This is just arithmetic. So 54 minus 441, and then minus 1269. So we are $399.69 in the hole already. So I'm just going to move my x-axis. Negative 399.69. that's where we're at so far. This whole thing is underground, underwater here. That's what we call it. Call it being upside down or being underwater. So we started off at negative 441. We're selling ice cream. We sold 18 gallons of ice cream. We're still underwater, right? We're still negative 3.99 and 69 cents. However, if we sell one more gallon, if we sell 19 gallons, then we can add $1.56, and that's called the margin or the margin of profit, to what we've already made, right? And we hope that this graph will keep going and going and going and get us out from being underwater. So it's sometimes interesting to not use calculus in the middle of a calculus problem, just to sort of set the temperature, the tone, to kind of see where we're at with the problem, so that your answer not only is correct, but in the grander scheme of things, makes sense. All right, so we're going to do more of this in the last two examples, and then that should be it for marginal analysis for now, until we learn some more calculus. We have to learn a few more techniques before we can make the business a little more interesting. The cost function for a company that sells gizmos is given by, and again, these problems are always a lot easier when the function is already given. So this is a quadratic cost function. Basically what it means is the cost to produce nothing is $9,000. $9,000. So your y is the cost. That's what this function means. And then as you create more, it kind of goes like this. It goes up, but it starts to get cheaper, right? The cost slows down as you produce more, which kind of makes sense. If you're producing 20 items, then the cost is going to be different than if you're producing 2,000 items, right? And so as you produce more, the cost to produce them goes down, right? Again, there is a science behind developing this formula, but what I'm doing is giving you an already created formula. Someday we'll get to the level where you have to create these formulas. We're not there yet. So I give it to you and I kind of tell you what it means as we go along. Right. But I do want you to be able to do calculus. So find the cost. Again, the total cost to produce 573 units. This doesn't require any calculus. Yeah. This is just arithmetic. Just plug in 573. So that'll be we don't need calculus, so just take this formula, negative 0.05 times 573 squared plus 60 times 573 plus 9,000. And write everything down in case you lose any of your data and your calculation. So 573 squared, a very large number, times 0.05. So that's negative 16,416 and 45 cents. 60 times 573 is 34,380. And then plus an additional 9,000. I usually do the middle minus the first. and then plus the last. It doesn't really matter the order, but I just have a habit of going from the middle to the left to the right. It's just an easy way to keep track of everything that I've done. I call it the BAC method. So B is the middle, A is the front, C is the last. This is positive. If cost is always positive, right? In your graph, there is no quadrant 4. Everything is in quadrant 1. Cost is always positive. All right, so that's how much it costs to produce 5. So I'm on my graph here, I'm going to say 573 units. The profit can be negative, but cost and revenue are always positive. And then this is my total is, what was it? 26,963.55. So that's my cost on the y-axis to produce 573 units. Okay. That's not even calculus. We could have done that in an algebra or an arithmetic course. Although I probably wouldn't put this in a basic math course, but college algebra courses is a good problem. All right, so now let's do some calculus. All right. Let's use marginal analysis. Which is a lot fancier sounding word than it really is. To find the cost to produce the 574th unit. So I want to know how much more, what's that little margin, this little margin here, just to produce the extra unit. One additional unit. How much is it going to cost me? Well, then I need the derivative. So C prime of x, that's our marginal cost. Multiply this by 2. You're going to get negative 0.10 x plus, and then the middle term is just 60. You drop the x, and then you always lose the constant. All right. Now remember, 574th is n. That's n. And so you want n minus 1. So you're actually going to plug in 573 to produce the 574th unit. So you back up 1. All right. N is 574, n minus 1 is 573. I don't really need a calculator to do this, do I? This is a 57.3 negative plus 60. I'll do it on a calculator just to be safe. $2.70. So, I mean, if you think about it, the grand scheme of things, this is an additional $2.70. That's the margin. You don't need to put 70. You just put 2.7. So, I mean, you've already spent, right, $26,000. $26,963.55, right? To produce 573 items. If you just make one more item, it's only going to cost you $2.70 more. And what you'll notice if you try these exercises repeatedly, you can try a different version if you're interested, it will get cheaper and cheaper and cheaper and cheaper as you go along. So as you go along, if I get maybe to 580, well, then it might only be $1.50 a unit. I get to 600, it might only be 85 cents a unit. And this cost will keep getting cheaper and cheaper and cheaper and cheaper and cheaper the more and more I make. Yeah. We hope it doesn't turn around the other way and start, going the other way. But we always try to stop at some optimal value, which we'll get to later. I only have time for one more example. I'm right at my time limit, but I'm going to make sure I do not have to film another part. So this will be our final example, example 10. So a small theater, well, maybe I won't say small. I'll just say a theater. Where can we make it? Let's put it on a theater holds concerts. So it's a big theater, concert hall. The maximum capacity is 3,900. I guess it's kind of small. Yeah. Medium size. I don't know what you call that. 3,900 people. The average attendance has been only 2,000 when tickets are priced at $20, $29. All right, so this theater holds 3,900 people. Only 2,000 people have been attending when tickets are priced at $29. Research shows that for every dollar that the price is reduced, this whole problem is going to take up the whole board. Revenue, oh no, not revenue, ticket sales. We'll get to revenue in a minute. An additional, how many people? 200 people are sold. So for every dollar that they reduce the price, an additional 200 tickets are sold. All right, so just some basic math here. If you lowered it to $28, then you would sell 2,200 tickets, right? Because people are cheap, right? They find out, oh, it's $1 off night, so 200 additional people go to the show. Find the marginal revenue function and use it to answer some questions. And I'm saying some questions because I don't have room to write all the questions here. All right, so this is just revenue. Yeah, we don't care about how much it's costing us to put on a concert, although that's another question we might have to answer at some point, but not today. So we just want to know the marginal revenue function, and then I'll end with maybe a couple comments on what that function can be used for. All right, we don't really need the max capacity right now. I'm just going to write it behind my head. Don't forget the max is 3,900. We're not going to use that until later in the question. What we're going to do is look at this. Yeah. So we're going to find a price demand function. P equals AX plus B, I guess you could say, or MX plus B, same thing. A is here for every dollar. That's -1, right? Every dollar that it's reduced, an additional positive 200 tickets are sold. So A is -1 over 200. So that's your A. It's in other words, it's the rate of change. Average rate of change. It's not a precise, it's not using calculus or anything. It's just using arithmetic. And you might want to double check. -1 divided by 200. Make sure you get the right number of zeros. I have done this problem myself and screwed it up by putting the wrong number of zeros. So that's your A. The B you don't know, but you can plug in 2,000 for X and 29 for P. So you get 29 equals -0.005 times 2,000 for X and leave the B as an unknown value. And you're going to solve this equation for B. So I still have my slope, or my average rate of change here. You can also call this M, but I've been using M for something else, so I'm calling it A. 2,000. So that gives me -10 plus B. This should always be a very easy equation to solve. Add 10 to both sides. And that's going to give you your B. 39. So now you don't need any of this other information anymore. Maybe I'll keep this here to say how I got the rate of change in case you're still getting caught up here. So now I have my price demand function is -0.005 x plus 39. Remember my goal. My goal is to find the marginal revenue function. I start with price, then I multiply it by X. You hopefully have seen this pattern before. The only difference between price, demand, and revenue is that the revenue has an additional X. Yeah, let's multiply all the terms by X. So this becomes X squared, and then that becomes 39X. You can do that mentally. Yeah. You don't actually have to write the step out. I mean, unless you want to. Times X, times X, times X. All right. And then our goal is the marginal revenue function. So the marginal rev is the derivative, R prime of X. Believe it or not, that's going to be the easiest part of the problem. You multiply the coefficient by 2. So -0.005 becomes -0.01. You lose one of the zeros. And then plus 39, and that loses its X. So there's your marginal revenue function. Now remember, we were only able to sell 2,000 tickets, right, on average. So we're trying to increase revenue. That's the goal, right? That's the goal of all these business problems, right? Minimize cost. We want to get the cheapest cost we can, and we want to maximize revenue. I mean, that's business in a nutshell, all right? So we would like to know, now, additional questions. What is the marginal revenue from selling just one more ticket? So just one more ticket, 2001st ticket. Excuse me. How much am I going to make if I can just squeeze out one more ticket? Well, remember, if 2001 is n, then n minus 1 is just 2,000. So we just plug 2,000 into this function. So that will be R prime of 2,000 So 2,000 times negative 0.01 is negative 20 plus 39, 19 additional dollars. So this is the additional revenue from selling the 2001st ticket. 19 additional dollars. And again, as you continue to sell more tickets, if you're lowering the price in order to draw in more people, right? You say, oh, let's lower it another dollar. Let's lower it another dollar. At some point, it's going to turn the other way and you'll stop making more money, right? That's what we're going to be focusing on in the next chapter. For now, we're just focusing on one little point at a time, but we should start to see the road ahead and kind of see the curve in the road and know when to put on the brakes, right? I mean, we're driving this revenue machine here. We should be paying attention to kind of where it's going, all right? Before I stop the video, I just want to say one more thing, and I've done a lot of the math ahead of time. This is more of just a think piece. Suppose the total revenue has already been given to you. We'll call this almost sold out show. Almost sold out show is $76,050. Almost sold out show means there's one seat left. Yeah, I remember our max capacity was 3,000. Right. So in other words, this is almost sold out. There's one open seat. How much revenue, or estimate the revenue from a sold out show? So I've already made $76,050. There's one seat open in the house, right? And I'm running the theater, and I'm like, I just want to fill that last seat, right? How much revenue am I going to get? Right? Is this going to go up substantially? What am I going to get? Let's see. So that would be the marginal revenue, yeah. For the 3,000 seats, I would put 2,999 seats, right? One seat is open. I don't want to plug in 3,000 because that means you've already sold out, right? You got to back up one step. You have one seat open and use the marginal revenue function to figure out how much additional revenue you're going to get from that one seat. So 2,999 2,999 times 1/100th. Yeah. All right, plus 39. Not bad. $9.01. Now, again, that's adding to the $76,050 that I already have. So the total revenue, estimated total revenue, a sold out show is $76,059.01. Well, that's it for marginal analysis. More to come, but before we can do that, we got to get into some new techniques in the next video. But that's it for this section. We'll move on to the next section. Until then, I'm Dr. Jordan. I'll see you on the internet.